Buffon's needle, and of course it's Buffon's straws here, so there they are. And I got a bunch more. I actually got a lot here in this box, but I'm not going to do all of these here, so here we go. And now, of course, I have to count them. All right, thank you. So this is Buffon's needle, and here he is, Gianluigi Buffon, goalie for Italy, who won the World Cup in 2006. And this one is Manuel Neuer, goalie for Germany, who won the World Cup in 2014. And then there is this other game where they played against each other, semi-final of the European Championships, where at halftime Buffon poked a needle into Neuer, which made him a little drowsy, so Germany lost that game. By the way, there are actually photos of the two together. It will be on friendly terms, but those would be copyrighted, and so I cannot put these in here, but from Wikipedia, this is just fine. And oh, wait a moment. No. This is not Buffon's needle. And of course, I just made up the story. So this one is the Comte of de Buffon, who was a naturalist in the 18th century, and he did a lot of interesting work there, and apparently one of them was what then became known as Buffon's needle and probability theory. All right, so let's go over there. So Apollo, please forgive me for my stupid story early on. So Buffon's needle, and this is where you drop the needle onto these parallel lines here, and this is how you do it. So there's a needle, and if it crosses, then you say it's a hit, and if it doesn't, it's not, and then you keep track of all the crosses and so on in this little table here. And what I'm going to do is I'm going to actually reload it here. And the theory part is toward the top. Actually, it's on here. It kind of implies it. It does say something about calculus here, how it's doing that. And here's the surprising result for this one. By dropping this needle over and over again, you come up with a probability, and the probability is linked to the number pi, 3.14. And the surprising thing is we're looking at a straight needle that is being dropped onto parallel lines, and for some reason we come up with the number pi that goes with the circle, relating the diameter of a circle to its circumference. How can that be? How can a circle number be connected to a straight needle and parallel lines? Well, it's actually right here, because the needle is gonna land down at a certain angle, and the angle measured in degrees, may that be 30 degrees, 25 degrees, 43.7 degrees, whatever, that actually connects this particular experiment to the circle. And again, this here would be the proof. Okay, your part of doing is the following my instructions. So I reloaded this one here, and so far I have drops of 0, 0, 0, 0 everywhere, right? The needle, by the way, is the same length as the distance between the parallel lines. It doesn't have to be, but it just makes it easy if it is. So notice I didn't click on anything, and here would be my instructions. Drop one needle 3 times. So let's see. There we go, there we go, there we go, and I think it crossed once. Right, number of hits, and a total 3 times, which means 2 times it didn't. Then drop 10, a total of 5 times, so 1, 2, 3, 4, 5, and of course you would have to count how many times are they actually crossing and how many times not. So out of the last 10, they crossed 7 times, and 3 times they didn't, right? These 3 here, they didn't cross. And because it just keeps on going here, I cannot look at the last 10 here. I would have had to keep track of that. But so far, I dropped 53 needles, 30 hits, and then makes a computation, an approximation of pi, 3.53, neighborhood, but not really that close, right? So this is where the law of large numbers comes in. So again, my instructions say, click on drop 100 7 times. 1, 2, 3, 4, 5, 6, 7 times. There we go. So here we go. These are my numbers. Oh, 3.21 is getting closer for pi, right? And now click on drop 1000 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times. 9 times, right? There we go. There we go. So, you know, if you have a few more or 100 or 1,000 more or what have you, it doesn't really matter. But in that neighborhood, right? Oh, look at mine. Right on, right? Well, do your own. By the way, I do like this applet here because of all these colors that are in here. So yes, do your own drops and record. All right, so here's the Monty Hall problem, and I'm really proud of myself that I have this centered so nicely with all these advertisements on this particular website. Okay, anyway, here we go. So the instructions that I give you is to pick any door and then stay on that door. So here we go, and then stay on the door. And it turns out it actually records when I keep the choice. Notice here, this time I want to go, right? So, and to repeat that 10 times. So I'm going to choose a door, I'm going to stay in a door. All right, this time I won. Choose a door, stay on the door, and 10 times, right? And it's going to be kind of random. So always stay on the door. Okay. Let's see, how many trials do I have so far? 6, right? Okay, now I got 8, 2 more. I always tried to click somewhere else, which is actually not true. All right, so by staying on there, apparently I won 4 times, and I lost 6 times. All right, so this time, change the choice. So I click on here, and I click on the only remaining closed door. Click on here, and I click on the only remaining, so I change. Okay, and this time I actually lost by changing, all right. Again, click on the only one, and of course, whenever I do that, whenever I click on a door, I have no idea, you know, my chance is 33% on the initial door. So as I said, always click on the door that is not yet opened. Click on the other closed door. So far by actually changing, I've won 4 times, 5 times now. There you go. But of course, I have no idea, you know, I could notice that I've been winning quite a bit by changing, but that's also kind of luck here, you know. I don't know that the car is over there. I didn't know that. So, okay, so it's as I expected. It should be to my benefit to change. However, not that drastically, okay? I'm just saying this should be a 67%. This is, of course, where the law of large number comes in statistics. So what I'm going to do now is I'm going to click the simulate button, and I'm going to change the run simulation to 1,000 times. Change the choice, because I personally have been for many, many years convinced by the answer that this will be to my benefit. I have to scroll up down or up a little bit here, and then do this instant. I tried this in Firefox, and it took actually not instantaneous. It actually took a few minutes. So let's see what happens here in Google. Yeah, this is really fast. I mean, notice how the numbers go up there, right? And it's a pretty, okay, it's not my expected 67%, but statistically it is way larger to change. All right? That means that my chances of changing really increase my odds. And yeah, you would have to do this. All right, so this is about the Monty Hall problem. And I'm not going to open doors with goats and cars and so on. Instead, I'm going to use playing cards. And Marilyn Voss Vant actually suggested cups with pebbles, so I don't do those either. I'm just going to do playing cards. I have 52 playing cards here and the jokers. And what I'm going to do is I'm going to have 3 cards each time. So 2 black ones and the red one. The red one is the winner, so that would be the car, and these here would be the goats. In order to do that, I'm going to take the 52 cards, and I'm going to take out all the diamonds and the 2 jokers, so they're gone. So I have 39 cards left. 26 of them are black, and 13 of them are red. And then I already put them into threes so that I can actually play the game over and over again. A total of actually 12 times. And I'll show you in just a moment why. So here I'm going to take the first 3 cards, I shuffle them, and then Mr. Reza is with me, and he's going to pick one of them. Go ahead, this one. All right. And I'm going to turn over one of the others, and here's the thing, I actually have to know, because I'm the quiz master, I actually have to know which one is the goat. So I'm going to turn this one over, and I told him he has to switch. So go ahead and switch this one. So it turns out in this case he actually would lose. There's the winner, right? And this was just our trial. So now I have actually 12 triples left. So I put all the others aside, and these are the 12 triples that I have left, which means if there is a 67% chance of winning by changing, we should get around 8 winners. If there's only 50% chance, we should only get 6 winners. Of course, the thing is, in statistics, in probability, there's the law of large numbers. And so we only have a small number. We only do it 12 times. So I don't know how the outcome is. We'll give it a try. So as I said, I actually have to know where is what. And so let's get started. There we go. So Reza, go ahead and pick that one. All right. I'm going to turn over a goat. You have to switch. So I'm going to turn this one over, and actually you lose. And there's the winner, by the way. Okay, that was the first one. So the first was a loss. Next one. There we go. Go ahead. All right. I'm going to turn over one of the others. You have to switch. Yep. This time you win. There's the other loser. Okay. So we have 1 win, 1 loss. Okay, go ahead. That one. All right. I'm going to turn over a goat, and you win by switching. So far 2 wins and 1 loss. Right. Go ahead. That one. All right. I'm going to turn over a goat. You switch. And it turns out that you lost. So how much do we have now? 2 wins and 2 losses, I believe. All right. There we go. Yep, switch. And you win. And here's the other goat, by the way. Right. 3 wins, 2 losses so far. Okay. All right, here's a goat. You switch, and there's the winner. So far, 4 wins and 2 losses. And of course, as you see, this is relatively slow, right? That's why I use that simulation there. Online, there we go, okay. So I'm going to turn over a goat, and that indeed is a winner. And there we go. So how much do we have now? 5 wins and 2 losses, I believe, if I kept count correctly. Right. Okay. Turn over a goat, and that is a loser. So we're at 5 and 3 right now. Oh, this is interesting. Probably the interesting part in just a moment. Oh, whoa, 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 whoa. No, I had 4 cards. I think that's what happened to me. All of a sudden, I had a wrong number of cards. Okay. I'm going to turn over a goat. You switch. and that's a winner. And I think we're at 6 and 3. Yeah, a moment ago I picked up too many cards. Okay, so there's the goat. You switch, and another winner. I believe we're at 7 and 3. Right. Right. There we go. So here's a goat. We switch. And it's a loser, so I think we're at 7 and 4. Well, finally, all right, I'm going to turn over a goat. And that indeed is the winner. So we're actually 8 and 4, actually. It's actually, for this particular experiment, it's exactly 67%, 8 out of a total of 12, times 1 by switching. Of course, it is the law of large numbers. This was only a small number, so you would have to really go to, well, as the simulation does, you can go up to 1,000 times. All right. Thank you.